And so the Gluon version of this is actually very, very brief. So the first thing I need to do is, well, I just load the data as before. Okay. And then I define my model. And I have the RNN module. And so RNN, number of hiddens, gives me a, well, RNN with 256 hidden units. RNN layer initialized just initializes it. So basically all the work that we did before is just those 3 lines. Okay, makes life easy, right? We still need to do a couple of other things though. So we need to, start it, right? So let's say mini batch size equals 2. We need to have an initial state. And so what we get is this. And so that's the mini batch size. That's the number of hidden units, 256, right? And that's what it outputs. Okay. And so what we can now do is we can look exactly what happens if I take, one step forward. And so, 35 steps means simply, I'm taking, a sequence of 35 and, producing this. And so this is exactly the same code as what we had before. This is just checking that the input and the output match in terms of shape. So the 2 states match, and the shape of the states also matches. Okay. All right, so this is really simple. Okay, and then, now that one's a little bit more complex. We need to define an RNN block. So the RNN block, okay, and so the reason why we need a block is because the RNN model itself just, deals with feeding data in and out. The block does the entire forward pass where you then, that knows how to, one-hot encode and do all the other convenience routines around it. So the first thing we need is, it needs to go and, construct the RNN layer. And then for the decoding and encoding, it needs to create this dense matrix. So that's just the constructor. Now for the forward pass, it's this one here, it needs to one-hot encode the inputs. Right. It then runs the RNN, and then it needs to generate the output, because the RNN doesn't know anything about that. Right, because we could have done anything bizarre here. And lastly, we go and just return the output in the state. And then we need another function begin state such that the RNN block knows how to start. Okay. Okay. Any questions so far? Yes?
So does Gluon automatically implement...
Sorry, can you speak up a little bit? It's...
Does Gluon automatically implement sequence sampling?
Sorry, I'm still...
Does it automatically implement sequence sampling? Or
No.
do you have to choose?
Okay, so the question was, does this do anything about the sequence sampling? No, not yet. So this is really just a mechanism of, well, here's a device where I feed it some data, and it produces some other state sequence from it, right? It doesn't actually do anything about preparing the input data yet, right? We'll still have to do that by hand, right? Or encode, obviously. But yeah. Okay, oops. That's the problem with hot corners. So for prediction, it looks very similar to before. The only thing is that, yeah, we now, call the RNN model. So that's the model here. So we initialize it. So begin state, that's exactly what we invoke. We generate our outputs where we're going to put things in. And then for all the characters in that sequence, okay, so we reshape it, and we just let the RNN take one step forward, right? This is basically because the RNN is just, the device to, generate the next object one at a time, whereas, then, and you can actually see that, for instance, here the decoding, this, through argmax, right? This is actually what converts it from a vector into characters again. Now, the if then else is exactly the same as what we had before, namely, if this is still part of, the original characters that I fed in to start with, it doesn't overwrite those, and it just copies them from input to output, and only after it's run out of characters that it was supposed to see in the beginning will it start producing new characters. So now there's an obvious question. Why on earth do we just let it process one character at a time, and then we don't actually care very much about the output there? Does anybody have a good idea as to why we would do such a wasteful thing? Right, because this is weird, right? Why don't I just start, after, the characters that I already know that exist? Okay, let me give you a hint. If I ignored the first few characters, right, and just started after those characters, would my model still take those characters into account? Would it still matter whether the first few characters are time traveler or chainsaw? Okay. I guess people are starting to shake their heads, right? It probably wouldn't matter then, right? And that's exactly the point. So if you were to ignore those first few characters, then your hidden state would not depend on those characters. So those first few steps are not wasteful. They are just there in order to load up the hidden state into something meaningful, right? That's the reason why I have to go and start with a meaningful hidden state. So if I wanted to have a better hidden state, I would simply ingest more. Okay, so, and then in the end, well, I just concatenate everything and that's it. So let's try and see. And this is exactly doing the same thing as what we did before. I started with Traveler and then have it produce another 10 characters, and those 10 characters are utterly useless because, well, yeah. Now, again, comes the slightly more complex function, and in the interest of time, I'll go through this only so much, and I strongly recommend that you look at those notebooks online afterwards. Okay, so let's look at that. Right, so we have a loss, which is softmax cross entropy. I initialize my model, and I invoke my trainer. Right, that's my optimization algorithm. Okay. Then you go through the data, for whatever number of epochs you have. This is just timing as before, and the only thing that I'm doing is I'm only using the consecutive data iterator because the other one turned out to be bad anyway, so no point in implementing both. And this train and predict RNN Gluon is a function that will come in very handy, for instance, also for your homework. You will end up calling this function quite a bit. So First thing is you initialize the state, right? As you would. And then you go with the data. And there's this funky thing that I'm doing here, which says s.detach. For s in state, detach. Right. So that just tells the autograd not to backpropagate beyond the boundaries of my mini batch. Right? So this is at the very beginning of a mini batch that I have this, and I'm just telling it, well, hey, anything you knew about state from before, drop that from the computational graph. Okay, we'll get to that in a lot more detail on Thursday, where we'll actually look at backprop through time and truncation and all those other tricks in quite a bit more. But for now, just trust me that this is doing something sensible. And then we do our usual training loop. So with autograd record, this is now it's game on. We produce output and state from the model. We take the y's and compare them through the loss function. Okay, once we have that, go and compute the gradient. Okay, take the parameter vectors, clip them, and then all you do is you just compute, one update from the trainer, update the loss function, and that's it. Okay, so that's really it. Now, the last thing, and I'm going to omit this, is this is really just monitoring to figure out what the perplexity is. For the homework, you will need to read that part. But the difference is, for the homework, you're actually going to implement something where you're going to measure the perplexity on an unseen test set. Right? Here we're just logging the perplexity on the training set. The difference is that in the homework, you'll have to keep training and test set separate. Short of that, it's going to be very similar. Okay. Any question? Okay, good. Then let's run. And maybe let's run it for more than 200 epochs. Let's maybe run it for 400. And let's see what happens. Okay. Any questions so far? Yes?
Is the procedure for using multiple GPUs the same as the one that was shown to us by Mu for convolutional neural networks?
Okay. Multiple GPUs in sequence models, it's close. Okay, so the basic idea is the same, right? You compute gradients for mini batches that are sent to different GPUs. Those different GPUs do their own thing, and then you get the gradients back. Okay, so that's the same. The problem is that essentially sequence models are much heavier on the CPU. Even the ones that use a lot of Gluon functionality. And that's not a big deal if you have a relatively slow GPU and a fast CPU. It can become a problem if you have like a P3 16x large with 8 GPUs. MXNet is pretty good with that, so the Python part is fairly lightweight, but it's non-trivial nonetheless. And there are cases where you can end up in a situation where it's essentially the CPU holding back the rest. This is why it requires a little bit more work. If you want to have a lot of detail about that, you should check out the latest Gluon NLP toolkit, which has parallel distributed training for the transformers for BERT. That's a highly non-trivial language model, and that will give you some idea of how to do this efficiently in parallel. Right. So, and most of the difficulty is really engineering in this case. But what we can see now is, well, first of all, it ran quite a bit faster, right? So you can see it's 0.15 seconds per pass. In the homework, the data set will be a lot larger. So this data set is around 140, 150,000 characters. On the homework, the data set will be 5 million characters because you're going to have fun with the collected works of Shakespeare. And then we can see whether your models can produce another Shakespeare, right? Or at least how close it'll get. Yeah, it's teamwork, homework, so don't worry too much. I mean, you can team up. Yeah. Any other questions? Okay, good then.